Okay. Well, it looks like we're a couple minutes after 9, and we'll get started. We've got people still logging in, but we've got a nice number already. So, welcome everybody to the Friday morning Bureau of Economic Geology seminar series, and we're really fortunate to have Jan Zalasiewicz. Did I say that right?
Yes.
Zalasiewicz.
Well there.
That's a hard one, I have to say. So Jan is an Emeritus Professor of Paleobiology at the University of Leicester, UK. So he's calling in from the UK, 3 in the afternoon, after tea time, I guess. Field geologist and paleontologist, he's taught Earth history to undergraduate and postgraduate students, undertaken stratigraphic studies ranging from the early Paleozoic to Anthropocene, and has written many technical studies and popular science works. And I'll just add on there, I'm sure he's going to touch that Jan has been part of the subcommission on quaternary stratigraphy, and really a multidisciplinary group that's been working on this issue for a long time. And clearly you can Google either many different means and find the technical, the volumes of technical works that Jan has participated in, as well as his popular books. I think I found about, I don't know, a couple dozen books, even very recently, that he's written, as well as magazine articles, Scientific American and others. And also, interestingly, there's been a curriculum that he supports called the Anthropocene curriculum. And so that's a really interesting topic as well. So I just wanted to add a little bit there to let folks know the breadth and depth that our speaker has come to us with. So thank you for joining us. And with that, I think we can share your screen.
Okay, that's great. Well, many thanks, Brian, for that introduction. And as you said, I've had a kind of Mark Twain style journey through geology. So I'm not quite sure what kind of geologist I am, but I do feel comfortable, in applied and economic geology, as that's probably where I spent most of my life, as a field mapper. So hopefully, this talk will, at least be partly in that flavor. Well, it's introducing this relatively new, quite controversial idea that we might be entering a new geologic epoch. And this, of course, is the context you're all familiar with. We have to deal with 4.5 billion years of geological time. That's far more than I can fit into my head. So the only way we can cope with it is to make it, bureaucratic and split, this enormous time into, sorry, it shouldn't have gone back there, units, which broadly represent phases or dynasties of Earth history, and which we have a fighting chance, of more or less keeping organized in our head as we navigate, through rock strata, and through the events that they represent. And that's, of course, 4.5 billion years, and we're currently in the top left corner of that, and we are formally still within the Holocene Epoch, which has recently been subdivided into 3 sub-epochs or sub-series. That, just 11,000 years, of which almost all of it is the Pleistocene, which is part of the Quaternary period, part of the Cenozoic era, 66 million years long, and in turn part of the 500 million year long Proterozoic aeon. So this, if you like, this kind of geometry of geologic time, is something that makes our lives as geologists possible in our work, and that is still formally the case. I have to emphasize, that and may indeed formally remain the case. But 22 years ago, indeed, in the year 2000, this man, Paul Crutzen, not a geologist, but a Nobel Prize-winning atmospheric chemist. He worked on the ozone layer, among many other things. made a suggestion. In fact, he was listening to discussion of global change in the Holocene as one of the meetings of the International Geosphere Biosphere Program, when his colleagues saw him becoming more irritated, and he suddenly said, "Stop the meeting!" And stop! Things have changed too much. The conditions of the Holocene no longer apply to us. We're in something else. And on the spot, he improvised the word Anthropocene. And really things caught on from there. I mean, he is an extremely influential scientist working within a very large community, of really Earth system scientists, oceanographers, climatologists, ecologists, biologists, and so forth, who floated essentially a geological idea that the Holocene had finished and something else had started. And that community began to use this term. He published it, indeed, the same year. And that community began to use the term in practice, in papers, to represent the industrialized present. Although Paul Crutzen himself initially suggested that this began about the Industrial Revolution, let's say, early 19th century, something like that. Their group of scientists also were recognizing another phenomenon. They were putting lots of data together on both socio-economic factors, such as gross domestic product and energy use and things like that, and also on Earth system trends, such as carbon dioxide levels and temperature and so on. And they recognized at the time something called the Great Acceleration, a marked upturn in the mid-20th century. And that is something we will see time and again, as we go through the kind of evidence of this talk. Be that as it may, the geologists, I think, as ever, were slow to the party in this, and only really began discussing this, 5 or 6 years later, when the term Anthropocene began to appear, in publications, of this large scientific group, in journals such as Science and others. And almost taking it as a matter of fact that this was real and formal. But of course, it may be real, but it wasn't formal in the way that the terms of the geological time scale are defined. So a group of geologists of the Geological Society of London published an initial paper suggesting only that this might be a possibility to add to the timescale. And on the back of that, a number of us were invited to form part of the ICS, the Anthropocene Working Group, to look at evidence as to whether the Anthropocene may or may not be real and may or may not be added to the geologic timescale. And we're coming up to some sort of conclusion in this. So this talk, in effect, puts the case for the prosecution for the Anthropocene. There's been a lot of work to do. I mean, whatever has been going on geologically, in the past few centuries, especially in the last 70 years or so, has not been simple, and a lot of it has been new and involved in new kinds of geology, including things like plastics, which are not, part of the classical range of things that we study. But nonetheless, a number of publications have come out, and the majority consensus of the group is that Paul Crutzen was right. The Anthropocene is real, and it should be formalized. I stress it hasn't been yet. It has many hurdles to pass, if it is to be. But this is the kind of way that the timescale would look if this comes to pass. So the Holocene would terminate about 70 years ago, so just one human lifetime ago, and to give an Anthropocene Epoch, and series at the top of that. And there's work going on a formal proposal on that, which I'll touch on, towards the end of this talk. So the work that's been done has been carried out, if you like, using as much as possible classical terms of reference and terms of description. So we think in terms of lithostratigraphy, chemostratigraphy, biostratigraphy, and so on, and put the evidence within that. And of course, we think of minerals and rocks first, and minerals form the basis of rocks, so we can take those. The term of reference here is a rather beautiful paper written by the mineralogist Bob Hazen and his colleagues some years ago, totting up, counting up the minerals on Earth and looking at their history. And there are about just over 5,000 natural minerals on Earth being identified and catalogued and classified on Earth. Only a few of these are the common rock-forming ones, and quite a few of them are vanishingly rare. But that is, if you like, the natural total. The left-hand diagram, which is a 5 billion year graph, shows that this number of minerals has not been constant, but has grown. So out there in outer space, there are only a few dozen very simple minerals. These grow as the planetary systems form. And if you examine, let's say, meteorites, as if you like, an early solar system sample, there are only about 250 minerals being recognized. And then a planet begins to grow, chemistry stretches out, and the number of minerals again then begins to grow as you begin to get on an Earth-like planet, igneous processes and metamorphism, plate tectonics and so forth. And on a dead planet, there was something below 2,000 minerals. And then when life arrived, and particularly when oxygen began to be free oxygen began to be a factor, then that created a whole lot of oxides and hydroxides, to give something in excess of 4,000 minerals 2.5 billion years ago, which has stayed more or less steady since then. And then the human effect. The human effect has been to create, well, not formal minerals, because they're not accepted as such, probably very sensibly, but there are now in excess of 200,000 mineral-like compounds, that is, inorganic crystalline compounds, which have been made in various material sciences laboratories, most of them, since the mid-20th century. The right-hand graph shows this growth in the number of new kinds of synthetic mineral, in inverted commas. So that is quite a big change. And if we look at examples of these minerals, well, they include the metals. There aren't that many metals as pure metals in nature. Gold is one of them, occasionally iron in meteorites and so forth, occasionally copper. But things like aluminium is vanishingly rare in nature, titanium also, and vanadium, molybdenum not found at all as far as I'm aware. And yet humans have begun to take these minerals, separate them out in very large amounts. So aluminium, for instance, there's now about 500 million tons of aluminium out there. Again, almost all since the mid-20th century. Enough to coat the whole of the USA and now part of Canada, in standard aluminium kitchen foil. So present in geological amounts, and iron, of course, is present, I think, there's about 30 times as much iron and steel as there is aluminium. Other things, something that might be called a mineraloid, plastics, synthetic inorganic polymer. And again, that has grown since about 1950, almost all of it. And there's about 9 going on 10 billion tons on Earth now, enough to wrap the Earth about twice now in cling film or plastic wrap in there. And already, as we now know, being washed around and blown around essentially all of the Earth's surface and entering strata. And there's now quite a large environmental plastic science going on. And one of the studies carried out recently, and again, these are all fairly recent studies, just the last, very few of them are more than 10 years old, of these plastic studies. This is the Santa Barbara Basin, this anoxic basin of California, where microplastics fragments begin to appear in the mid-20th century, and the number of them grows as in higher layers, again mimicking the growth of plastics worldwide. So it's a new, if you like, a new rock component. And of those rocks, and again, the strata made from minerals, one large fact about them now is just how much, if you like, human-made rock sediment there is. In a recent study by Zalasiewicz and colleagues, worked out that the amount of rock and soil that we've shifted and seafloor sediment has grown again enormously, since the mid-20th century, and the movement of sediment across the planet is now very strongly human-dominated. So, if you like, natural processes, river transport, beach transport, is only a few percent now of total sediment transport. And another example of this kind of thing, just one component of this, the rock and soil that we shift and transform in urban construction and in mineral production. Again, that has grown from a few billion tons earlier in the last century to nearly 1/3 of a trillion tons annually now. So we're simply creating a whole lot of new kinds of rock, new kinds of strata, which can be mapped. And again, this is, even 30 odd years when I was a geological survey mapper, I was putting stuff like this on a geological map. The urban strata, made ground, artificial ground, that now makes up a large part of urban geological maps. And again, one of the recognizable parts of the younger part of this, which is the post mid-20th century part, is concrete, which has been made since Roman times, but which only really has been made in large amounts, again, since that post-World War II, mid-20th century times, since when there's been about 1/2 a trillion tons being made, which is about a kilo of concrete per every square meter of the earth, land and sea. And even if you like, in what one might call natural, in inverted commas, sediment, one can see changes. So here is a deep sea core off the coast of Madagascar, and there's a long record, nearly 20,000 years of very thin carbonate oozes, and then suddenly on the top of that, there lands a lot of siliciclastic mud, which is the result of deforestation in the hinterland, increased sediment transport, and so on. And this kind of thing, again, is a more complicated signal, but this kind of thing is fairly common worldwide. So that's something of, if you like, the physical rock stroke strata. There are a number of different kinds of chemistry. Of course, the carbon cycle is the headline part of chemostratigraphy, and again, partly due to human energy needs being still mostly satisfied by the burning of hydrocarbons. And again, this graph shows the enormous increase in this hydrocarbon extraction and burning since the mid-20th century. So yes, it did start long ago, but it only became significant sometime after the Industrial Revolution, that mid-19th century, and then the mid-20th century. Nearly 90% of coal, oil, and gas has been burnt. And as we all know, that is having an effect on climate, on atmospheric composition. So CO2 levels have been climbing, as this graph shows, from its systematic measurement starting in the late 1950s and gradually and still consistently climbing. How much of that? I mean, that's parts per million, which again, I can't really imagine in my head what that means. But if you break those now 130 extra ppm of carbon dioxide and convert that into pure gas at atmospheric temperature and pressure, that's a layer of, if you like, industrial carbon dioxide about a meter thick around the Earth. So waist height to an adult, head height to a child, and growing currently at about a millimeter every 2 weeks in that. So I feel like that's the physical reality of that carbon. And again, if you translate that into geological history, then this graph shows the rise of carbon dioxide. The bottom blue line, the dark blue line, shows the rise in CO2 from about 180 to about 250 to 80 ppm in the across the Pleistocene Holocene boundary, and then this very sharp rise in the last century or so. And then geologically, we can always see the carbon isotope value. We're burning isotopically light carbon. So there's been an equally abrupt carbon isotope shift and an anomaly seen by that yellow going on red line. So that's a mark that is currently being left in strata of different kinds. And again, we can put that in an even longer context, courtesy of Antarctic ice with fossil air in air bubbles. And so here is one of these classic 400,000-year records of carbon dioxide going up and down, again, between about 180 to 80 ppm, between glacials and interglacials, and then rising very suddenly, to something now about 415 ppm. Humans have been around for most of this time, but with precious little effect, on the environment. Those detectable impacts, forest clearance, large mammal extinctions, and so on, began to be noticed about 50,000 years ago and have been gradually increasing. But this sudden, overwhelming impact is much more recent, and that is what we're equating with the Anthropocene. So it's not human impact per se in total, but it is a planetary change caused by a threshold in human impact being reached. And again, as is in the news pretty well every day now, that is having an impact on climate. So there's been about a degree rise in temperature over the past century or so, which is still a modest rise in temperature, but again, compared with the rise between the Pleistocene and the Holocene, it's a much more abrupt one. in that. And of course, its temperature is still rising. And again, the physical reality of that is something that, I try quite hard to understand, because as a field geologist, I don't immediately appreciate the meaning of graphs and numbers. But if you translate the kind of heat gain by the ocean, most of this extra heat is going into the ocean. It's the equivalent of pouring in about 4 billion cups of hot tea, sorry, a very English analogy there, into the sea every second. So that is the kind of heat buildup that is going on, and which will have a long-term impact. We don't yet know how much carbon dioxide will end up in the atmosphere. That is a matter of very many factors, or therefore how high temperature will rise. But because of the long lifetime of carbon dioxide in the atmosphere, those effects will be felt for very many thousands of years into the future. And of course, one of the effects, again, is very much in the news, is the heating of the air in the oceans, the melting of ice caps and ice sheets. And again, after about 3,000 years of almost complete stability of sea level, within 10 centimeters or so, sea level has begun to climb, by, a geologically trivial, 20 to 30 centimeters so far. But again, this is a kind of built-in rise, which will carry on for some time yet, no matter what we do with carbon emissions. And of course, because there's a lot of Holocene landscape, delta tops and coastal plains and so forth, which make up inhabited landscapes, that is now part of the landscape that might become part of the seascape, over coming decades and centuries. And a kind of long-term geological signal might look something like this. That's the Triassic-Jurassic transition in a lovely section near Bristol in the Severn Channel. The red terrestrial Triassic muds being overlain by the pale grey retic deposits, and then the early Jurassic marine black shales on the very top as a potentially analogous, far future Anthropocene signal. And then others as well, other kinds of stratigraphic signals. One is simply the unburnt bits of carbon, particulate carbon from industrial smoke. Under the microscope, that looks something like this: fly ash particles, or spherical carbonaceous particles, as they're known. They're quite distinctive. There's nothing quite like them in geology. They're produced by high temperature combustion, industrial combustion of hydrocarbons. And they can be treated in the same way as pollen grains. They can be analyzed in sediment samples. And I have colleagues who do this now as the main part of their working lives. And that's another stratigraphic section. This is from northern England, and a peat bog, about 1,000-year record, showing on the left these SCPs, the fly ash particles, beginning to appear during the Industrial Revolution, and then really taking off in this mid-20th century, together with lead and iron and things. And again, that has been equated with an Anthropocene stratigraphic signal. And it's been replicated around the world. This is work done by Neil Rose, who spent a lifetime, he's still doing this, chasing around the world looking for fly ash in recent lake deposits and estuary deposits. And it's a global signal. The red line is the 1950. In all of those 70 odd stratigraphic sections from around the world. And it's another way to recognize Anthropocene strata. Others as well, nitrogen and phosphate, something else that that is changing, perhaps in percentage terms, even more greatly than the carbon cycle. So the amount of reactive nitrogen and phosphorus, mainly for fertilizers, has more than doubled since the mid-20th century. And that signal can be picked up in different ways. One of the indirect ways is the way that fertilizer washed out to sea creates plankton blooms, as in the red and green patches in the Gulf of Mexico here. And when they sink and decay, they produce now extensive dead zones across the seafloor, which kills off, all multicellular life. Currently, this is mainly seasonal, and it's affecting places like the Baltic Sea, I said the Gulf of Mexico, Chesapeake Bay, and others. And that again, in far future time, if it develops, might give you signals comparable, with these dark stripes in the chalk here, the ocean anoxic event deposits of the Cretaceous. There's a way to go yet before that, but that is a potential analogy. But other things, I mean, these one can analyze these recent strata and find in them, in both marine deposits and terrestrial deposits, things like pesticides, DDT, dieldrin, aldrin, and other persistent organic pollutants. And again, there's a kind of a mid-20th century origin and increase for many of these, which form part of the Anthropocene sedimentary fingerprint. And perhaps most sharply is the fingerprint from radionuclides, released by mainly by the bomb tests, and particularly the thermonuclear, the very big bomb test of the early 1950s to 1960s, which means that all the sedimentary layers, us as well, are marked by things like cesium, americium, plutonium, and so forth. Biostratigraphy. Now I'm more than half, I guess, a paleontologist myself, in that, so the fossil side is something where there's also an Anthropocene signal, and trace fossils might be started with. Here's a Cambrian example. These are some creature creating a trace on a Cambrian seafloor. It looks very much like a Saturday night trace, but on there, our equivalent, which is a thing easily washed away. But here's another trace fossil, which is one of my favorites. It's the thing in the center. It's about the size of an acorn. It's a fossilized wasp's nest in a paleosol in Tenerife, in a volcanic paleosol, made by the wasp building a home for itself out of little bits of pumice. So here we have other analogies. This one is called Shanghai, but of course there's also Houston, London, Nottingham, Paris, and so forth. We create biologically made complex rock, metal, glass structures, both above ground and below ground. And of course, these are large now, hard-wearing, especially the below ground examples, and affect now several percent of the land surface. That's what's being called anthroturbation. Biostratigraphy. There's something else, more classical biostratigraphy is body fossils. And the big question here is really, are we in another mass extinction event of the kind we can see at the Permo-Triassic boundary, for instance, or the Cretaceous Tertiary boundary? And this is a question that's been examined by a number of scientists, including Tony Barnowski and others, over several years. And the upshot is not yet. There's only perhaps 1, 2, 3 species, percent of species of most groups known to be extinct. But there are very many others which are now in very small numbers and endangered or critically endangered. And the number of extinctions has been rising sharply. It's very hard to measure, but nonetheless, there's been a clear inflection, in the rate of extinction over the last century or two, which again is clearly carrying on. So again, this is largely a prospective signal of the Anthropocene, but one that is already present, and that is not a future signal, is the one being created, not by the extinction of species, but by their translocation, from one continent to another and one ocean to another, by invasive species, or sometimes called neobiota. And there are lots of examples of these, so the classic ones are things like the rabbit, originally from Iberia, then made itself at home in Britain, Australia, many other places, and is clearly beginning to leave a fossil record. The rat, of course, is another classic example, but also things which make more traditional fossils. So this is a zebra mussel, originally from Eastern Asia, in the last century, migrating across much of Europe, including to Britain, where it's become extremely numerous in waterways, and over the last 20 to 30 years, entering the United States and Canada, and again, as you can see, migrating very quickly and becoming very abundant in many lakes and rivers. So this is one that humans moved inadvertently. This is one that's been moved advertently because it's delicious. The Pacific oyster, again, originally from Asia, but that's been transplanted and now forms and has escaped from its oyster forms to become a worldwide species now, again, of a robust fossilizable kind. And invasive species now are comparable in number to native species in many, if not most, parts of the world. And so there's been a homogenization, of the Earth's biology, a breaking down of biogeographic barriers, which have been in place for tens or hundreds of millions of years. And it's a resetting of biology, and therefore a resetting of future paleontology. Already there is a signal, already being used by colleagues of mine to try and track the Anthropocene. And as one part of this, we have, if you like, numerical assemblage changes, differences in the biomass of different species. And we can take terrestrial vertebrates, for instance, and we're currently, as humans, we're very successful, very numerous. We're about a third by weight of terrestrial vertebrate biomass. Most of the rest of that is the animals we keep, to eat, basically, as domestic animals. They're about 2/3. Wildlife, by comparison, is now less than 5%, probably less than 3% of that. So that's again a big assemblage change, and within that there are also, if you like, fossilizable, if you like, changes in the kind of species we as paleontologists can recognize. A species recognized by shape, not by genetics. So the Anthropocene chicken is something that has become very much bigger. It's been 3 or 4 times the weight, with a much larger and different shaped skeleton, again, by intensive breeding in the last 50, 60 years or so. And it's become by far the most common bird in the world. By biomass, most birds in the world are now chickens, supermarket chickens. And again, fossilizable in that sense. At a larger scale, there's, if you like, the planetary scale. The biosphere is being changed, and has been changed for a long time. Thousands of years. For thousands of years, humans have been essentially cutting down forests, reducing the amount of biomass, perhaps halving it, if you like, from its pre-human, pre-civilization level, down to about just over 1 trillion tons. Now, and one can compare that with something that's been called technological mass, or human-made mass. All the things that we make to live in or to travel in, ships and cars, buildings, skyscrapers, roads, and so forth. And this mass, anthropogenic mass, has been measured, by a lot of statistics, and again has grown from just being a few percent of biomass just 70 years ago to very recently becoming greater than biomass. So human-made mass, all the things we make and use are in active use, are now greater than biomass on the planet. And that has been linked to a concept called the technosphere, analogous to the biosphere, which represents, all of life and its interactions. So Peter Haff, based at Duke University, has this idea of the technosphere of all technology, and us who make it and nominally control it, who depend on it, have this idea of the technosphere. And one of the things about technosphere is it's very physically, it's very heavy, and most of it is waste. Of the stuff that we build, we use, throw away in different ways, or that. So our cities make up, again, mostly the rubble beneath the cities. The artificial ground makes up about 11 trillion tons, and one can count in, things like, croplands and, plowed fields and such like. Altogether, that's about 30 trillion tons in weight. Which is equivalent to about 50 kilos of stuff, mainly discarded rubble, per meter squared of the Earth's surface, land and sea. So if you like, as a stratum, we are roughly ankle deep in the Anthropocene on average on Earth. And of course, the technosphere is evolving very quickly, rather more quickly. Much more quickly than the biosphere is, through things you might call technofossils, of which a classic example, is the evolution of the mobile phone, in just 30 years. My own is embarrassingly near the top left-hand side of that, I'm afraid. And of course, things are still moving. Since Paul Crutzen suggested the Anthropocene, the physical evidence, for this change to the planet, which may or may not be formalized, has grown to CO2 has risen, temperature has risen. The number of motor vehicles on Earth extraordinarily has trebled. The amount of plastics have doubled, and so on. And this is still, if you like, that trajectory is still carrying on. So what are we going to do about it? Well, we suggest, controversially, for all its brevity and all its unfamiliarity in using evidence such as plastics and concrete, that it might be formalized, and it might be formalized by a classical golden spike within recent strata. And again, even more extraordinarily, this is being funded by a humanities institute, the Haus der Kulturen der Welt in Berlin, which is funding this very technical science, very head-banging science work, who also are the people behind the Anthropocene curriculum that Brian mentioned. So they're taking this concept, and doing lots of things with it. So we have about a dozen potential golden spike sites being studied around the world, and some in lakes. I mean, estuaries, in speleothems, peat bogs, and such. And the work on that is coming to some sort of conclusion. And by the end of the year, some decision should be arrived at as to which, is the best one to represent the Anthropocene. But here are a couple of examples. Here's a beautifully laminated lake deposit, Crawford Lake in Ontario. And again, you can see the beautiful lamination. You can count the layers year by year. And there are all kinds of signals, the radionuclide signal, and that the main graph shows the fly ash signal, which shows the classic, mid-20th century spike in it. And here's another one. Here's the Baltic Sea, Gotland of the Baltic Sea, worked on by another team. And again, on the right-hand side, you can see lots of graphs of different things, microplastics, organic content, different kinds of chemistry, americium at the bottom. And again, all of them show, an inflection or a spike to make Anthropocene strata characteristic and recognizable, and traceable and correlatable around the Earth. So this is the kind of thing that we have. The Anthropocene is clearly real, as a recent and rather dramatic change to planetary geological conditions. It's different from, the standard, rather stable Holocene baseline. And it will clearly have long-term consequences. You can recognize it geologically, and as I say, there will be a proposal put forward based on a classical golden spike to try and add it to the geological time scale. So I leave, with the question, are we really living in a different kind of Earth from that represented by the Holocene? And we'll leave you with a sunset, an Anthropocene sunset, with a jet contrail up there in the sky. And happy to take any questions of yours.
Great, thank you, Jan. That was amazing. Really to see everything pulled together like that. I really enjoyed that. We've got one question in the chat. So if folks do have questions, you can put them in the chat, or you can maybe raise your hand and unmute yourself. This one's from Joe Bell. He asks, would the rapid death of coral reefs count as a marker? Is there an acceleration or deceleration of rock material since life would become rock and since the reef would no longer grow?
Yeah, it's a great question. And it's one of these difficult questions because for sure, coral reefs, look to be seriously endangered, and if temperature rises by another, degree or two, then, they'll look. Paradoxically, or perhaps poetically, two of our sites we're looking at are coral sites. We're looking at two. There are two. There's one in the Atlantic, in the Caribbean. One off Australia. Two Parietes corals which have annual layering, and which show very nice signals. They pick up the radiocarbon signal very well from that. So they record a Holocene Anthropocene transition while themselves being endangered by the ongoing effects of the Anthropocene, in the near future, within a generation or two. And in fact, one of the lead scientists of one of the studies, said in an email, she does not expect coral reefs to survive, in any meaningful way. So she's doing the work as a kind of a archive of something she already considers as in the past on that. So yes, and the same might be applied to even to things like ice cores, surface ice cores. There are increasingly numbers of melt events affecting them. So it's a beautiful question. and I flounder for an answer, but that's the best I can provide.
That's great. Thank you. Here's another question from Michael Young here at the Bureau. I may have missed this in the talk, but to what extent has land surface globally been altered through the variety of human activities? And is that included as part of the criteria? I think you did show a few slides on some of that material.
Yes, we mainly try and translate it into lithostratigraphy rather into geographic change, but of course you use both when mapping, so most of the mapping I did, was feature mapping, so one would, I recall, mapping accumulations, things like, waste heaps and embankments and things like that. But the main work that's been done, at least within our group, has been to try to tot up the amount of mass that's present in each of those categories. Do those calculations over time, that is over the past century or two, and then compare, if you like, present trajectory with a more past historical trajectory. And those do show that, say, most reshaping of the landscape now is human rather than that done by natural process of erosion, almost by an order of magnitude now.
And here's a question from Julie. It says, when do you expect the proposal will come out, and will it specify an exact year or decade for the switch from the Holocene to the Anthropocene Epoch?
We expect that by the end of the year, we hope to have made a decision, because we're in a way, we're being driven by the very kind but very demanding funding, of the HKW in Berlin, who would like, this process to be part, within their timescale, their program. So we're working very hard to have a decision by the end of the year, so it can be within, they can help advertise it, promote it, discuss it, and then it passes on to the Quaternary subcommission. At that, who will then have to spend some time getting their heads around, this, I say, this rather different kind of data, this unfamiliar set of stratigraphic proxy trends, and then scratch their heads over it and wonder whether to accept it or not.
Here's a question from Rich Ketchum. Says, can you discuss the types and bases of opposition to the idea of Anthropocene?
Yes, it's there is a significant opposition. It's really divided opinion among geologists. Some like the idea a lot, others hate it, and there are a few in between. But I think it's more polarizing than that. The kind of geological objections are, one, it's very short. I mean, 70 years is not, to many geologists, a geological time frame. It's unfinished. It doesn't, it has arrived at no stable state yet. It's simply a state different from the Holocene. But whatever it might emerge as is probably still far in the future. There are others who would wish to use the name Anthropocene to denote all human impacts upon the biosphere. This is not so much geologists, but anthropologists, archaeologists are often using the name to go right back, even 50,000 years, to look at the impacts on, forest clearance and large mammal extinctions and so forth in that. And they say history is a continuous process, and they are not used to the kind of sharply synchronous global boundaries that we have in chronostratigraphy. So there are a whole lot of objections being raised. And as a group, the Anthropocene Working Group has spent a lot of time answering those, using those objections as a, if you like, as a springboard, to take it. It's a new idea. It has to have bricks thrown at it, and whatever is left after that, might serve some purpose. So among geologists, it's not at all guaranteed that it will survive the scrutiny. At each step, along the ICS scrutiny, it's got to pass by supermajority, more than 60%. So these are tough barriers for a very different, say, very brief, plasticky, concretey kind of epoch.
Great. Here's a question from Marcy Phillips. How much influence do invasive species have on an Anthropocene assignment? If it is significant, I wonder if it is being applied, quote, fairly relative to the past geologic time when we've seen species adapt to a changing environment and considered it a generally positive quality of survival.
Yes, I think they certainly invasive species often get a bad press because invasive and because they often elbow out other species. But some ecologists have said that given that the Earth is warming up, and will undoubtedly warm it further, some invasive species might actually be the key to functional ecologies of the future if they're better adapted to those kinds of conditions. Certainly, invasive species, the trouble with them as stratigraphy is that they're very complicated. They form local signals, of the kind that, say, quaternary biostratigraphers use, and with different local signals, in different continents and different parts of continents. But nonetheless, given the amount of change that's going on, and that is, adaptation will take place, but that adaptation will be with permanent change to biological communities and therefore future fossil communities.
Okay, there's another question here from Julie. Would the group declare a specific year, like 1955, yes, or a decade, mid-50s, or event, 1945, first nuclear test, for the date of the change, or something else?
Certainly a specific year. I mean, the quality, of the stratigraphic records we're looking at is often so good that, well, you can recognize individual years. And if you're looking at those corals, you can recognize individual months. So I suspect it will be, there will be a golden spike selected to a year, which may be 1952 or 1947 or 1955, whichever is found to be, the most suitable. And probably there will be, it will be something like the beginning of that year will be chosen to integrate geological history with human history, so you can make the term more easily transferable.
Okay, I have a question, another question from Joe Bell I missed earlier. It says, maybe too ambitious, but since the changes are so appreciable, so distinct, why not shoot broader and make the Anthropocene something larger than an epoch?
That's it's another great question, and that has been suggested, even up to the the era level, in publications. I think, especially given the opposition, and the doubts about the Anthropocene, by amongst geologists and others, we're being classically scientifically conservative about this. Yes, we do recognize some of the changes are now taking the planet out of a quaternary kind of system, not just a Holocene Earth system, but nonetheless, being cautious. One can say, Holocene conditions have definitely ended, and that for the time being, that seems, a first step. Of course, down the line, that may change, especially if the changes keep on intensifying.
Okay, I think that's all the questions from the chat room. If there's anybody online who'd like to unmute themselves, we're approaching an hour now, so we'll respect Jan's time here. I had just a quick question from your both the technical and then just applying this to more the general public, the term Anthropocene, and you see it used in lots of different contexts. What are your general thoughts on just that term, whether it's in an event or it's an epoch, or used as a verb, or
Yes.
what are your general thoughts on just how this has evolved. And
yes, the word itself, I mean, it took off partly because, you know, the anthropo, you know, gave it such a, it has a kind of visceral impact on people. So I think that has helped. But it's also, in some ways, it's a bit misleading because it's a change of the planet. And it doesn't really matter what causes changes, you know, lithostratigraphic, chemo and biostratigraphic. It just matters that the change, you know, is there, you know, is large enough to be equivalent to some of the big changes of the past. And the fact that humans are causing it, you know, is in some ways quite beside the point. But of course, you know, it's easy to think, you know, it's equivalent to human-made changes or all human-made changes. You know, so let's say the event idea, which has been published recently and which we've recently responded to, has the Anthropocene going back 50,000 or more years as encompassing all human-made change, you know, and not having a, you know, having a, like a fuzzy beginning and being, you know, variably interpretable. Yes, the word itself is, you know, it's a kind of double-edged sword, you know, and you know, we've had to write about its different meanings as well in that. But we hope that it will stabilize, you know, at this more precise meaning, you know, of this more restricted and characteristic time interval.
Yeah. Well, Jan, thank you so much for your time today and really fascinating talk. I really appreciate that. And we'll, like I say, we're over an hour now, so we'll give you back the rest of your afternoon. And thank you for joining us, and thank you on behalf of the University of Texas at Austin. We really appreciate that. So
okay, well, it's been a great pleasure joining you all, and you know, all the best to you all, and you know, I hope the weather calms for you a little bit over the next day or two.
Great, thank you, Jan.
Okay, all the best. Bye.
Bye. Cheers.